Hello. In this video, I just want to hopefully make some connections for you. And they come from what I believe is a difference in the approach at the very beginning of the course in trigonometry on how to present the trigonometric functions. So I present this a little bit differently from your author, and because of that, my videos are a little bit perhaps awkward for the first two chapters, and then after that we converge. All right. So I want to see if I can make some connections for you that hopefully will also help you to not have to memorize certain charts or tables that I see in the book in the first chapter. All right. So first I want to kind of mention, I have this blurb here on your home page how important trigonometry is and where it's used in so many applications, you know, GPS, oceanography, architecture, engineering, really so much more. But if I were to give you sort of a really broad brushstroke of what are the fortes of trigonometry, although there are many, it would be two things: indirect measurement, and what that means is I can't actually touch the length of the thing I'm trying to measure. All right, I can't touch it. Like maybe it's the height of a tree and I don't want to climb the tree, or maybe, as you see here, the diameter of the sun. I can't do it, right? But I can still measure it. It's just done indirectly. I can't directly touch it. So that's a huge forte, though. And then through equations to model things that are cyclical and repetitive that happen over and over and over again. So we'll come back to that. But things like that, obviously waves, sunlight during a season at a particular location on the earth, even the breath, the volume of breath in your lungs, how you metabolize a medication, so on and so forth. It goes, you know, and then you take the medication again in your body, your liver processes it, and so on and so forth. But it's cyclical, right? So that's the big brushstroke, the very broad brushstroke. Now, I'm going to go through what I use as an approach so you understand why the videos are the way they are, and then I'm going to connect them to certain parts of the book in the first chapter that I see. All right. Now, first of all, everything that we study up through chapter 6, so that's all the way up through chapter 6. It's only in chapter 7 that we go to basically all triangles. But all the way from chapter 1 through chapter 6, it's right triangle trigonometry. And what that means is you have some kind of, you know, angle, right? But you have a right triangle. So there's your right angle. All right, and that's really the majority of the book. So that's going to be a 90-degree angle where a vertical and a horizontal line meet. Now, where this trigonometry developed first was that it was used to be able to indirectly measure in a free-form way. So what I mean by that is, I don't want to go into this in too much depth, but essentially what you had is, for a particular angle, and you have a right triangle, let's say that's my angle, I just standardize what I call the names of the sides of the right triangle in relation to the angle. So in relation to this angle, across from it is the opposite side. Across from the right angle is the hypotenuse. And then this side is adjacent to the angle. Okay. And then once you name the sides in this way, when you think about ratios, since there's only 2 sides per ratio and there's 3 sides total, there's only 6 ways that you can combine that, right? You can say the hypotenuse with the opposite, hypotenuse with adjacent. Or you could say opposite with the hypotenuse, opposite to adjacent, or adjacent to opposite, adjacent to hypotenuse, right? Where the first one that I start with is the numerator and the second one's the denominator. So there's only 6 possible ratios, and those are your 6 trig functions, okay? Now, with freeform trigonometry, the idea is you can have your right triangle represent something that you're trying to indirectly measure, but it can be in any orientation. So I could be standing at the top of a building, right? And maybe I'm looking down and I want to know, I don't know, maybe I know this length and I want to know this length. So in that case, my angle is here, and relative to that angle, this is the opposite because it's opposite or across from that angle. Here's your vertical and horizontal line, so here's your hypotenuse, and then here's the adjacent side, right? So you would pick the two, whatever you have to know. Let's say you know this side and you want to know that side, so you'd pick the trig ratio that involves the opposite and the adjacent, right? So I just want to make the point that, first of all, these trigonometric ratios, when you start out using what I call freeform triangles, right triangles, everything is in relation to the angle, right? So in this case, here's my opposite. If I were working with instead like this angle, then relative to this angle alpha, this is the opposite, right? That's opposite, this is adjacent, and always across from the right angle is hypotenuse. So first of all, it does matter what angle you're referring everything to. And then it doesn't matter what orientation your right triangle is. I could have a right triangle something like, I don't know, this, and there's my right triangle, and maybe I pick this angle, So it doesn't matter. I could move that around however you want. But essentially what happened then is we defined, now so this is in your book on page 48, these ratio of the sides, like opposite hypotenuse and adjacent hypotenuse and so on and so forth, the 6 possible ways you could combine those 3 sides into ratios. We gave them names, and one of the most famous ways that we know of, that I know of, to put these together is SOHCAHTOA. So that's, SOHCAHTOA. So that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, right? So that's where you're seeing this. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, and so on and so forth. So you need to commit those to memory very quickly, because that's going to make your life way easier. And when I say commit to memory, I do not mean that you kind of sort of know it on Thursdays after 5 o'clock. I mean I can wake you up in the middle of the night and go, what's the definition of sine? You go, opposite over hypotenuse. I mean like that. I mean you really know it. That's going to make your life a lot easier. Now what happens is, with this freeform triangle, essentially you're representing something in nature or some physical situation with a right triangle. And then, so for example, let's say this is a tree, right? And you're looking at what's the height of the tree, and I don't want to have to climb the tree, and I'm standing over here, right? And I sight the tree, right? And basically this is my angle, and I sight it as whatever angle I get. Here's my right triangle, and I know I can walk this distance, so I can measure it, but I want to know this distance. So opposite and then adjacent, that's going to be tangent. Tangent of that angle is stored. Now that's the real key here. We already now know, or have tabulated, the 6 different trigonometric ratio values for every angle. So if that angle turns out to be, let's say, 30 degrees, then I know that what is the ratio of the tangent of 30 degrees. It's some value, and I say, oh, what's that value, and I can use it. Okay. So if you want to learn what you want to do is definitely watch. If you want to know a lot more about this, this is one of the most important videos I can direct you to. It's in section 1.3 videos. It's similar triangles to trigonometric ratios. It goes much more in depth into this and explains, how these 6 arose and how they're related to each other, how to use them, and the point of similar triangles moving on into trigonometric ratios. Okay, so there's your freeform triangles. Now what happens is, in trigonometry, there's a point where we move from free-form right triangles into the circle, all right? So what happens is there's a definition, and it really comes down to this definition, by the way. Don't complicate it. It really is this. You take whatever rotation you have, you drop a perpendicular line, and that's a symbol for perpendicular, to the x-axis. And therefore the angle that you're going to work with is between the terminal side, That's where you stopped rotation, and I'll show you an example. And the x-axis. Okay, so what I mean by that is, let's say here's a circle and I'm putting an xy axis on there so you can see it. If I rotate just in the first quadrant, then that means I rotated starting at 0. I rotated here in the positive direction. Positive, it's counterclockwise. Negative is clockwise. So I rotated here. This is my terminal side. All right. At that point where you meet the circle, drop a perpendicular to the x-axis. There's my right angle. Here's the angle I'm talking about. So this is opposite, adjacent, and hypotenuse. Okay. Now what you'll notice is, to reach this point, I have to move over in the xy, right? So if I were to give this point on the circle an xy paired coordinate, this is x, this is y. Notice that adjacent is x and opposite is y. Now let's suppose I rotate more. I rotate to the second quadrant. So this is the actual angle. The actual angle is this rotation right here. Here's my terminal side. I drop, according to the definition, the perpendicular to the x-axis. There's my right angle. And between the terminal side, which is this, and the x-axis is my angle. So there's my angle. Notice across from the angle is opposite. That's the length of this side. Didn't do it very well. Here's adjacent. Here's hypotenuse across from the 90-degree angle. And notice again, if I have an xy, x is adjacent, y is opposite. So, does this stay the same for all quadrants? Yes, it does. So essentially what happens is then that because of this definition, that is the reason why, your SOHCAHTOA, which is, you know, the opposite over hypotenuse and adjacent over hypotenuse and all that, becomes now opposite is y, adjacent is x, and that'll always be true. So now you can redefine all your trig functions in terms of x, y, and r, because you've standardized the process of representing an angle on the unit circle, or the circle, by dropping the perpendicular to the x-axis. That's what's happened. And so now you get these definitions. However, these are actually presented to you much earlier in your book, page 23, as opposed to page 48. So I kind of wanted you to understand that connection, though. All right. And then what happens is, if this makes sense to you, then what happens is, let me go ahead and show you couple other charts that I'm hoping will make more sense to you now, knowing these definitions. Now again, you'd have to commit this to memory so it really makes sense, but honestly, if you know these definitions and then you understand you just drop a perpendicular to the x-axis, you can see by the picture that opposite is y and adjacent is x, and so on and so forth. So these would just fall right out. But here's the thing. If you're told something like, hey, let's look at the circle, let's just look at a circle, and you say, all right, here's x, y, always this is 0, going counterclockwise is positive, going clockwise is negative direction. Well, what happens is, when I go to define a right triangle, let's say I rotate almost to here, right? So I'm rotating all the way over here. I drop to the x-axis. Notice that what I have here, here's my right angle, here's the angle that's the reference angle for this particular angle, this rotation. Notice it's almost all vertical and very, very little horizontal. So it's almost all y and almost no x. So if you were to know that the radius of this circle is 1, you could actually go ahead and label these 4 points here, right? You'd say this is all x, so 1, 0. Over here, there's no x, it's all vertical. Here it's in the negative direction, all x, and then here it's no x, but all vertical in the negative direction, assuming this is, of course, 0, 0, sorry, where the axes intersect. Well, what that means is, if I have, as I keep rotating, you can see here that this triangle is getting slimmer and slimmer. Eventually, you have a triangle that doesn't really exist, but it's like a vertical line. So if you were going to, let's say, look at the definition, for example, of tangent, right? What you'd have is y over x, right? So the y would be here, x. When I say tangent, in this case of 90 degrees, right? Here's 0, 90, keep going, 180, 270, and finally back at 0, but having done one revolution, 360. Tangent of 90 degrees is defined as the y coordinate over the x coordinate, but we know that would be what? 1 over 0. Well, it honestly doesn't matter how big or small the circle is, because you're dividing by 0, what are you getting? Undefined, right? So what you can see is there's, depending on which sides you're looking at, right? You can see why you'd have some of these ratios become undefined, right? But again, for me, instead of memorizing this chart, I would have a hard time memorizing this. And for you, maybe some people would want to memorize this. So it's just however you learn. I would, rather than working with this, I would rather just draw myself a picture and go ahead and quickly label the quadrant, values here, like 1, 0, 0, 1, and so on and so forth. And then knowing the definition of the ratios, I know which ones are going to be undefined or which ones are going to be 0, right? So that's again, I think something that would make it easier understanding how all this is put together, rather than seeing this right, and going, wait, where's this coming from? I have to memorize it. You can see where it's coming from, right? And then another chart that I kind of wanted to go over with you is here, right? And that's on page 31, and it talks about here, whatever quadrant you're in, the different functions, trig functions, and whether they're positive and negative. Again, I don't really want to memorize. Again, that's just me. So the only things I really have to know is this, right? I really have to memorize this, and I can draw myself a picture or memorize the x, y, and r, which you're probably better off memorizing this because it's so fundamental, right? But if I know these really well, then if you say to me, okay, I'm in quadrant, for example, 2, right? And in quadrant 2, I know that x is what? Negative, and y is positive. So therefore, if you ask me, well, what about tangent, which is y over x, right? So if you say tangent of whatever angle, which is y over x, well, the y is always positive, the x is always negative, so I'm going to have positive divided by negative. Well, a positive number divided by a negative number is always negative, right? So then you'd see that tangent in quadrant 2, right, here's tangent, quadrant 2 is always negative, right there. Or let's say I'm here in quadrant 4, and you're asking me about sine of an angle. Well, I know, again, because I've memorized these definitions so well, I know that sine is y over r, but in this case, I want to use the unit circle. R is 1, and so a length of 1. Sine of an angle is y over r, but it's really just y over 1, which is y. Well, the y coordinate in quadrant 4 is what? Well, x is positive and y is negative. So in this case, in quadrant 4, sine of an angle is always negative. And so, oops, sorry. Sine in quadrant 4 is always negative. There you go, all right? And I did want to mention also that I talk about the unit circle, but I just want to show you that if I have concentric circles, right? And here's my XY axis. For any particular angle, if I rotate a certain amount, right, I drop my perpendicular to the x-axis, well, I can drop that perpendicular from whichever circle I'm on. And if I'm going to look at, for example, I'm going to have some help from our cat, my cat here. If I look, for example, here's my angle, and I say, what's the tangent of the angle? Sorry, but you gotta go. And that's y over x. Well, that means I have the ratio of this y value, right, this length to this length. But it's also, the ratio is the same. The lengths aren't. Oh, you gotta go, baby. But the ratios are the same, right? Because why? They're the similar triangles, right? All the angles are the same, therefore, corresponding ratios of corresponding sides are going to be the same. So the ratio of this to this is going to be the same as the ratio of this to this. So therefore, you have that, for that angle, you know what the tangent of that angle is. And it doesn't matter what circle you're on. So what we do is we say, well, let's make it easy and let's use the unit circle where the radius is 1, so that some of my denominators will be 1, and that's much easier. Okay. And lastly, the last point I want to make is where we connect to here. I gotta move around my cat. I mentioned to you that the second very important forte of trig is the representation of cyclical processes. Well, here's the idea. If I look, for example, at the sine function, right, on a unit circle, And I know that the sine of an angle is the y-coordinate, essentially. Well, here I start out, remember, I start out all x and no y, and I go to all y. Let me put these in here, not think too loud. Get myself confused. But if I look at, although I could have like a triangle here and, you know, bring down my perpendicular. If I look at just the y values, right, I start at none, then it gets a little bit bigger, gets a little bit bigger, then it gets a little bit bigger, until finally it maxes out here, right, meaning the length of the y coordinate of the particular right triangle that I'm working with. And then what happens is I keep rotating, right, I rotate over here, then my y coordinate gets what? Shorter and shorter until it gets to 0. Then it becomes what? Negative, all the way max negative, and then it gets smaller and smaller and goes back to 0. So we'll represent this graphically is, given particular angle, what's the y coordinate? It ends up starting at 0, then it goes to a max, then it comes back down, right? So it's getting bigger until it gets to the max here. Then it's positive, it's getting smaller, positive getting smaller. Then it's getting bigger but negative, so it comes down here. And then it's all the way negative, and then it starts going less negative and goes back to 0, right? But if you keep going around the circle over and over again, you get this. So there's your repetition. There's your wave. So again, that's what I just wanted to point out. It's just some really big concepts about trig and make some connections for you that I hope will make this a little bit easier for you as you work through chapters 1 and 2, where some of my videos don't quite go in sync. But hopefully this will help that happen. Thank you so much for listening.